Hello grade 12s, and welcome to another video from the answer series. This is video 5 in the chapter Work, Energy and Power. In this video, we will remind ourselves of mechanical energy from grade 10 and then derive the work energy theorem. We have already hinted at the equivalence of energy and work. We see this in the ability of a body to do work, because it has energy, and in the change in energy of an object when work is done on it. Both are measured in joules. Objects have mechanical energy because they are moving, and because of their position in the gravitational field of the Earth. We have equations for calculating potential energy and kinetic energy. Remind yourself of the symbols that we use in these equations and their meaning. To find the total mechanical energy, add the potential and kinetic energies together. If a net force acts on an object, the acceleration cannot be equal to 0, so the velocity changes, and therefore the kinetic energy of the object will also change. We can show this by taking Newton's second law and multiplying by delta x on both sides. We take an equation of motion and rearrange it to get an expression for the acceleration times delta x. That can get substituted into our rearranged Newton equation, and out comes an expression for the change in the kinetic energy of an object. This shows us that if there is a non-zero net force, it does net work equal to the change in the kinetic energy. This leads us to the statement of the work energy theorem, in words and as an equation. Candidates are often asked to state the work energy theorem in the final exam, in which case, here is the text of that definition. Now we have three ways of finding the net work done on an object by all the forces acting on that object at the same time. They are the sum of works, the definition of work, and now we can add the work energy theorem. These expressions can be combined. So, the sum of works is equal to the change in kinetic energy, or the product of the net force and the delta x is equal to the change in kinetic energy. If asked to state the work energy theorem, the next question is highly likely to be solved using it. What should you remember to do? Well, start with a free body diagram. What you do next depends on the information available. You might be able to find F net from a sum of forces, or W net from the change in kinetic energy, or even from a sum of works. So, list all the given values, write down the essential statement of the work energy theorem, that is, W net equals delta EK, and expand from there. Substitute and calculate the answer asked of you. Finally, ask yourself, is this a sensible answer to the question? When we derived the work energy theorem, you saw me use an equation of motion. You can often use equations of motion in energy calculations. However, if the question says use energy principles, then you are limited to using the work energy theorem, the work definition, sum of works, and, where appropriate, conservation of mechanical energy. Here is a worked example to show you what I mean. Sipho and Bongi have moved the crate about 12 meters. It is accelerating from rest, so the initial velocity is 0 meters per second and the final velocity is 8 meters per second. First things first. Here is the free body diagram. Let's add in delta x. We will use the angles between the forces and delta x rather than the horizontal components when doing the calculation. Secondly, the normal force and the gravitational force are perpendicular to delta x, so they do no work. Here is the list of values given or extracted from the question. We calculate the work done by Sipho and Bongi separately, using the work definition. Sipho's force is 750 newtons at an angle of 310 degrees to delta x. Bongi's force is 500 newtons at an angle of 30 degrees to delta x. For part 4, we use the work energy equation. The initial and final velocities are substituted to get a net work of 4,480 joules. Be careful to remember to square the velocities. Finally, because the sum of works equals the net work, we can get an expression for the work done by the frictional force. Substitute all the previous values into the expression. So the net work will go here, Sipho's work will go here, and Bongi's work will go here, to get a final answer of minus 6,501,24 joules. Is this answer sensible? Yes. We expect friction to do negative work, and the magnitude is the right size for the problem.
If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.